Hey everybody, welcome back. So what we're going to do is continue looking at image formation by a positive lens, but this time what we're going to do is we're going to look at how it can form a virtual image being used as a magnifier. So this is another simple optical system using a single positive lens. We'll go ahead and get the slideshow started. Again, this is in the same PowerPoint document, thin lenses. Okay, so we've already talked about how a single positive lens can form a real image configured as a camera or a projector. Now what we're going to do is we're going to move the object inside that front focal point, in between the focal point and the lens, and see that we get what we call the simple magnifier or magnifying glass. So here you go. I've just drawn the same lens with its two focal points, and you can see I've put the object inside the focal point, in between the front focal point and the lens. Now we'll go ahead and do regular old ray trace. And again, I invite you guys to stop the video and you try the ray trace and see what happens to your rays. Did you do it? Okay, let's see what happens. Here's that first ray, parallel to the optic axis. We know what happens to that one. It goes through the back focal point. And the second ray we know is going to go right through the middle of the lens. And that's it, right? So now we look at these rays and something interesting happens. They are diverging. With the camera and the projector, with the object outside the front focal point, they converge to give us real images. So now what do? To find out where that virtual image is located, just like with the plane mirror, we trace these diverging rays backwards, and they appear to come from this point right here, so that must be the tip of the image arrow, and there it is. There is our virtual image. So what do we get when we use the single positive lens as a magnifier? We get a virtual non-inverted image. It's oriented upright, just like the object is, and it will be bigger than the object. That's the whole point of the magnifier. Okay, so next question is, oh, no, it's not yet. I'm sorry. I'm going to label the standard quantities here. So here's the object distance, right, from object to lens. Here is the image distance from lens to image. Notice that it is going to be a negative image distance when you have a magnifier. And then we have H and H prime, just like they're normally defined. Okay, so Q will be negative. Oh, and before we get to that question, if you want to see this image, where is your eye? Where does your eye have to be? Your eye, or a camera lens, has to catch some of these diverging rays. So your eye is going to be over here. Although I realize, excuse me, in my slide, I've put this eye too far to the right. It doesn't look like it's going to catch any of the rays that would come through that lens. So I really should move this eye closer to the lens, but the point is that your eye has to catch some of these diverging rays, and then you will see the image, this virtual image, as if it were located here. We're going to talk more about this when we talk about the eye, but I wanted to point out that what really happens is the rays that enter your pupil, well, they're going to hit the cornea first. These diverging rays, they're going to get refracted, bent by the cornea. They're going to go through through your pupil. They're going to then go through the lens of your eye, and those rays are going to be converged by the cornea and lens combination. So you do get a real image formed on your retina, but your brain interprets that to be this virtual image. Okay, so it's not like super magic is happening and these rays are diverging and somehow you see this virtual image. The rays actually do get focused and form by the cornea lens combination onto your retina and form a real image. Okay, now here comes the question I wanted to ask. So how much bigger than the object does the image appear to us if we're looking through this magnifying glass? And you might think the question is, oh, it's just the lateral magnification, H prime over H. But that only tells half the story. So when we're dealing with virtual image and we ask how big does this appear to you, the lateral magnification is not what you should look at. we have to formulate something called the angular magnification. And we'll do that on the next slide. But the reason we have to do this is, if you think about it, like for instance, as an example, look at your finger. Just put your index finger straight up and look at it. Now, if you move it farther from your eye, I think you'll agree it looks smaller. You haven't changed the lateral dimension of it, its height. What you've changed is how far it is from your eye. So how big this image, this virtual image, is going to look is going to depend not just on h prime, but also on that distance q. As I say right here, it's going to depend on h prime and how far it is from the lens. I put absolute value signs there because q is a negative value if we pay attention to its sign. The lateral magnification only incorporates h prime, right? H prime over h. The angular magnification is going to incorporate both lateral dimension and distance. So we have to formulate that. So let's go ahead and formulate the angular magnification. First thing we need to establish is, what do we mean by a near point? So the near point for your eye is, how close can you put something from your eye, measured from your eye, so that it is still in focus? Because you want something to look as big as it can be, but you want it to be in focus. That defines the near point. Now, if you have a healthy eye, average healthy eye, that's taken to be 25 centimeters, the NP. So we're going to take that as a given. Healthy near point is 25 centimeters. It may be slightly different for your eye. We're going to take it to be 25 centimeters. So here's what we'll do. Let's suppose we take an object of height h and we put it at the healthy near point from your eye. Now, if I draw a line from the tip of that arrow to the optic axis right here, where it intersects your eye, I'm going to form an angle. I'll call it theta naught. Now, what happens to that angle if I increase this distance of 25 centimeters? If I take the same object and move it farther from your eye, I'm going to decrease the angle, theta naught, from this point right here at your eye to the tip of that arrow. Notice that the object will also appear smaller to you. Similarly, if I make, let's say I have this at 25 centimeters and I make h bigger, well, the object will look bigger to you. Notice that the angle theta naught will go up. So looking at this angle right here, that's a good way to get both the lateral dimension and the distance from your eye in one value. And the bigger it gets, the bigger the object appears to your eye. So we're going to do a similar thing when we're viewing the object through the magnifying glass. So when I view this through the magnifying glass, to use it properly, I'm going to put it less than 25 centimeters, usually much less, from the lens. So my P is going to be much less than 25 centimeters. I'll form a virtual image with that lens, and with my eye right next to the lens, we'll assume I'm looking at that virtual image. Notice that if I draw a line, and it's this dashed purple line, from the tip of that arrow to the intersection point of the optic axis and the lens, I form a triangle, similar to the triangle I formed over here, but this angle theta is going to be bigger than this theta naught. So that's what we want. We want this angle to be bigger than theta naught. So what we'll do is we'll formulate the angular magnification to be this angle theta over this theta naught. Okay? Again, measured from the tip of the image arrow, measured from the tip of the object arrow here. So this is the definition of the angular magnification. Now, I agree, if you might be thinking this, that this is all fine and good, but this is sort of a pain to figure out, because who wants to try to figure out angles for an imaging system? What we can do, with the help of some trig, is we can recast this formula in a more useful form. So what I'm going to do, guys, I'm first going to look at this triangle over here, this right triangle on the left, and I can say that the tangent of theta naught is h over 25 centimeters, but this angle is going to be relatively small, so I'm going to use the small angle approximation. The tangent of theta naught is going to be close to theta naught if we use radians. I'm also going to look at this triangle over here, the HP purple hypotenuse triangle. Because that angle theta, that's the same angle that's formed with this larger triangle, the image H prime Q triangle. So if I look at that smaller triangle, I can say that the tangent of theta is h over p. And then again, since that angle is going to be relatively small in practice, that's approximately theta in radians. So what I can do is I can replace the theta and the theta naught with h over p and h over 25 centimeters, and I get a much more friendly equation to use to calculate the angular magnification for this lens. It's 25 centimeters over the object distance. Okay? Very nice. Now, next thing we're going to do, we're going to talk about what we mean by the maximum useful magnification. So I have a lens, right? If I want to use it as a magnifying glass, what's the biggest magnification I can get from that lens? And the image is still in focus. It's not blurry. Well, if we think about it, what's another way of asking that is, what's the closest you can get this image to the lens without it looking blurry? Well, assuming your eye is right next to the lens, that's when this Q distance is 25 centimeters, the healthy near point. So what we want to do is we want Q to be negative 25 centimeters to get the maximum useful magnification. Negative again because Q is pointing to the left. So if I take my thin lens equation and I stick in negative 25 centimeters for my Q, I can solve for 1 over P. I get this expression. Well, what I do is I take 1 over F plus 1 over 25 centimeters and I stick it into the 1 over P up in this equation, because this is 25 centimeters times 1 over P, and that leads to this equation for the maximum angular magnification that you can get for a lens. Useful magnification. You can actually form the image closer than 25 centimeters from the lens, and you will get a larger magnification. It'll look bigger, but it's going to be blurry. So the useful maximum magnification is given by this formula. Okay, you don't have to memorize the formula, of course, but it's a useful one. And notice that it has the focal length explicitly in it. So you can see that the shorter the focal length of the lens, the larger useful magnification you can get from that lens used as a magnifying glass. So more curved, shorter focal length lenses are going to be better magnifiers. Okay, one thing I want to point out, this is just sort of a neat thing to point out. The lateral magnification, which is h prime over h or minus q over p, in general, that's not going to give you the same value as the angular magnification for the magnifier, the magnifying glass. The angular magnification is what matters. You don't really care about the lateral magnification because that doesn't give you the full story. However, if you're using the lens to get the maximum useful magnification, so Q you know is negative 25 centimeters, it turns out that the lateral magnification will be equal in value to the angular magnification. If you don't have the maximum useful magnification for little m, big M won't agree with it. I just point that out. Okay, what I want to do now is I want to do an example problem to show you how these calculations look and also to compare the lateral and the angular. And then I got a great joke for you dealing with angular magnification. So bear with me. Okay, so I've switched over to my notebook here, and here's the example problem we're going to look at. Suppose you have a lens with a focal length of 5 centimeters, plus 5 centimeters. You're going to use it as a magnifying glass. And we're going to look at a bug, let's say, that's 1 centimeter long. Okay? All right, so the first question we're going to ask is, how far is the lens from the bug if you're using this to get the maximum useful magnification? So let me come down here. Whoops. And let's answer A. All right, so I know that my focal length is 5 centimeters. How far is the lens from the bug? What I'm really looking for then would be the object distance. Okay, so I have two ways I could do this. I could use the thin lens equation directly to solve for P. I know F is 5 centimeters, and I also know that if I'm getting the maximum useful magnification, Q is going to be negative 25 centimeters. Okay, so I know that Q is negative 25 centimeters. So I could stick that in there and solve for P, and you should get the answer, which is 4.1 centimeters. But the other way you could do this is you could say, look, that equation that we just went over, I know that the maximum useful magnification, angular magnification I can get is 25 centimeters over f plus 1. So I put in 5 centimeters for my focal length, I get a magnification of 6. But I also know that I can always find the angular magnification using 25 centimeters over p. So if I just set that equal to 6, I can solve for p and I get 4.17 centimeters. So either way would work. Okay, let's try to answer the next question. B, what is the maximum useful magnification? I just did that, right? It's 6. Yeah, but if you had done answered A by using the thin lens equation, you wouldn't have calculated little m. So if you have P, right, you can find little m by using 25 centimeters over P. And sometimes people like to write it as 6x, 6 times when they're talking about the magnification. Okay, what's the next question? What is the lateral magnification? So we can come down here and say, okay, now we're after big M, which just looks at the ratio of h prime to h, but it's more useful, usually it's more useful, in my experience, to remember that as minus q over p, right? And we know that q is negative 25 centimeters, so this is going to be 25 centimeters over p, which in fact is equal to the angular mag. So the lateral mag is also 6. Yeah, we just went over that. If you're getting the maximum useful angular magnification, the two mags are going to agree. Okay? Now the next question is, well, how long does the bug look to you? Well, both magnifications are giving us 6x. So if you looked at either of those would tell you it's 6 centimeters. All right, but I'm telling you, it's always the angular magnification that'll give you the correct answer. Okay, in this case, the lateral mag will also give you the correct answer, but that's just because we have q equals negative 25 centimeters. In fact, to emphasize that difference, what we're going to do next is let's move the lens just a little bit, just a smidgen, like 6 millimeters or so that now, it's 4.8 centimeters from the bug. So what we're doing then is we're making in E, we're making P be 4.8 centimeters. So E asks, how far is the image now of the bug from you? Well, to answer that, I would use the thin lens equation because we're no longer going to have the same magnification. So I would go to 1 over f is 1 over p plus 1 over q, right? You know f is 5 centimeters, p is 4.8. You can solve for q. Okay, now when you do this, you will find out, and you can double check, that q is negative 120 centimeters. So now the image of the bug is 120 centimeters away from you, over a meter away from you. Before it was 25 centimeters from you. Okay, interesting. F, what is the angular magnification now? So let's come over here and do F. So what is the angular magnification? Well, I always can use 25 centimeters over P. That's the safe equation to always use. I know P is 4.8, so if I take 25 over 4.8, units cancel, I'm going to get 5.2, positive 5.2. G, what is the lateral magnification now? Well, if I calculate the lateral magnification minus Q over P, I'm going to have negative minus 120 centimeters over 4.8 centimeters. That's going to give me a whopping plus 25x. Which is the correct value to use to answer H? How long does the bug look to you now? This is a magnifying glass. We have to go with the angular magnification. It's 5.2 centimeters because we're getting 5.2x from our magnifying glass. You see, the lateral magnification has led you astray. It's only looking at the ratio of h prime to h, and that is indeed 25. Okay, so what's happening is, if I go back to my, oops, I'm so sorry. If I go back to my PowerPoint, what's happening is before this image, right, was formed 25 centimeters from us, right, now what's happening is it's being formed way over on the left. The actual height of the arrow is really large. It's 25 times longer than the object. But because it is so far away from us now, right, it only appears 5.2 times larger. So it's the angular magnification that matters. All right. Okay. Let me end that show and go back. Whoops. Go back to the notebook. All right. So the answer is 5.2 centimeters. All right. That's a fun example. All right. Now, here's my joke. I know you want to end this video, but I'm going to tell you a real quick joke about angular magnification. There are two lions, and they're walking along the savannah, and they look back. Oh, no, I'm sorry. I already messed up the joke. Let me try that again. There are two zebras. Now I got it. Two zebras walking along, and they look back, and they see a lion starting to chase them. Now, the lion's really far away. So they start running, and they're running and running and running, and they keep looking back, and the lion is gaining on them. Gaining, gaining, gaining. And pretty soon, the lion is right behind the two zebras. So the one zebra says to the other, "Kick her, kick her." And the other zebra says, "I can't kick her. I've known her since she was that big." That meaning really small. I known her since she was tiny. Get it? It works better if you could see me holding my fingers really close together. But that's an angular magnification joke. Thank you. Thank you very much. I'll end. Bye-bye.